Okay, so chapter 21, we talk about the birth of stars and the discovery of planets outside the solar system. Talk about star formation, how the HR diagram relates to that, evidence that planets form around other stars, exoplanets, what we're learning about them, and new perspectives on planet formation in the 21st century. Okay, so this is a really wonderful little passage here. Giordano Bruno, famous for not only his books but also his Italian food. Anyway, in this book, he talks about how there are countless suns, the stars, and countless Earths orbiting the suns. He had no way to know that, of course, at the time, but he thought that was the case. It seems obvious, and it's turning out to be true more and more. Anyway, he was tried for heresy and burned at the stake in the year 1600. So people don't like, the elites. All right, so 10 to 12 million Kelvin. That is the temperature that you need to achieve it before stellar fusion can take place, where hydrogen begins to be fused into helium. So every star on the main sequence, HR diagram, main sequence down there, every star that's on the main sequence at the time, which means its brightness and temperature correspond to these points on this line, that's called a main sequence star. And only stars that have temperatures of 10 to 12 million Kelvin in the core will lead to ignition, and that's when you get a star. Okay, so how does that happen? How do you get that? There's the basics of stellar formation here. Is that main sequence stars like the sun, they generate energy through nuclear fusion for billions of years. They are turning hydrogen into helium. So eventually they will run out of fuel after they burn through all the hydrogen. There's different masses of stars from about 10% to about 200 times the mass of the sun. There's more low mass than high mass stars. The most massive stars, type O, are also the most luminous and have the highest surface temperature, and the lowest mass stars are the least luminous and the coolest. So remember, OB, a fine girl, kiss me, OBAFGKM. Type O is the highest mass star, type M is the lowest mass star. Okay, so and the Milky Way contains enough to make billions of stars from gas and dust. So what is the process of star formation? So this image here is called the Pillars of Creation. And if you zoom way up on the top of that image, then you can see this stellar nursery. And this is very dense gas collapsing under gravity, and stars are being formed among this gas as we speak today. So molecular clouds are the stellar nurseries where stars are born. The two things you need, gravity and pressure, are what allows the gas, as it collapses in under gravity, that increase in pressure and temperature is what leads to ignition. This is pretty cool. There's the Orion Nebula down here, and there it is again in infrared. So you can see it's very bright, a lot of heat being generated as stars are being formed there. Okay, another zoom in of the Orion Nebula in different wavelengths there. So you can see here the central region of the Orion Nebula in B is the infrared light, and A is visible light. So remember, visible light gets absorbed by gas and dust, so it's hard to see through it. But in visible, look at these baby stars here, and there they are, very bright, being formed right there in infrared. So you can see star-forming regions right there. Okay, Westerlund 2, really cool image. Look at this, all these stars, all the different colors, all the different, there's a bunch of them there. Continuing to form in that region. So star forming, how does it work? You've got a cloud of gas, a molecular cloud. It collapses down and forms what are called protostars, and then eventually they could turn into full stars or brown dwarfs or other things. And then over time, the blue stars, notice these images as you go further and further into the future, you get fewer and fewer blue stars because the hot stars don't live as long, so they die out, leaving a bunch of red stars left over. Look at all these red stars. Okay, so your red stars do not last nearly as long. The blue stars do not last nearly as long as the red stars. Okay, so the idea here is you start with a region of gas. Okay, you could have a molecular cloud, which is gigantic, but a region about 5,000 AU. Remember, 1 AU is the average distance from the Earth to the Sun. About 5,000 AU, that starts to collapse under self-gravity. So it just gets squeezed into itself. And when that happens, it starts to form this disk as it starts to rotate. And then as this falls in, you get this energy radiating out. And then you could get this region where it becomes very hot, and you end up with a protostar starting to form. This is pretty cool. So one thing to note here is that there's still this ring of matter, this disk. So the reason this forms is because of conservation of angular momentum. So as things start to rotate, if you take a sphere, a solid sphere, and you start to rotate it, it will start to spin around like that, and eventually as the sphere rotates, it becomes more and more and more flat. So if you spin a basketball, the center of it will start to bulge out a little bit, and the basketball will turn into more of an egg shape. Now, the reason it doesn't completely go that way is because it's a rigid object. But if you have something like Play-Doh and you start spinning it, you'll see, or pizza dough, how do you make pizza? By spinning it, by tossing and rotating it. It will flatten out because of conservation of angular momentum. So the same thing here. As it starts to collapse, it collapses down and it will start to rotate. And once it starts to rotate, whatever direction it starts to rotate, it will end up with this disk. Now, the important thing is that disk, that flat pizza there of gas and dust, blocks light out. And you can see here, these are pictures of a baby star, and you can see there's a star hidden among these, so right there's a star in the center of this cloud, and you can see these jets of energy shooting out from top and bottom, but there's that ring of gas and dust obscuring the star itself. And this ring of gas and dust is where the planets are going to form. And you can see over time, 95, 1998, 2000, you can see over time the jet is changing. Okay, and so why does that happen? That happens because as this rotates down, it gets very hot here, and then at the center, the rotation is very tight, but the jets that come out of it, the energy that goes up, isn't trapped in this disk here, so it's freely allowed to just shoot up like that. Okay, so yeah, this is really cool. These are outflows from protostars again, gas and dust coming out of a protostar. There's some other baby, the disks. So there's a disk there, there's a disk here, the disk there, disk here, disk there. This one is hard to tell where the disk is. It could be this and that. I don't really know where the disk is in that picture. It's gotta be here. Okay, so so these are all stars, protostars being formed, and baby solar systems being formed. This is what our solar system looked like at one time, where you have a thick cloud of gas and dust, and then light leaking out over the tops and at the sides, and those are called protostars, and the rotating disk of gas and dust, and that's what eventually turns into a solar system. Okay, so the HR diagram can be used to determine the evolution of a star. So remember, the HR diagram is plotting luminosity versus surface temperature. And the main sequence, when a star begins fusing hydrogen, its brightness and its color or temperature, which is the same thing, is going to follow on this line. So for example, the sun is 1 solar mass. Draw that over here, bing. That means its surface temperature is about 5,000 Kelvin. Okay, and so that's how this HR diagram works. Now, before a star fuses hydrogen, it could be here on the main sequence. It could be here or not there. or here, or there, or here, or there, or there. Well, it turns out that the temperature of the protostar will determine its it will determine its evolutionary track. So basically, how much mass the protostar begins with will determine where it ends up on the main sequence. So we can tell by looking at a protostar what star it will eventually turn into, and when we can follow its brightness as it. So basically, in this case, this star, whatever this is, since it moves straight over on the HR diagram, that means its brightness does not change. Its brightness is staying constant because the Y value does not change as we go back and forth. But what happens to the surface temperature? It goes from 4,000 to 10,000 to 25,000 to 30,000 Kelvin as the star forms. Okay, so this is an interesting way that we can determine the evolutionary track of a star. So in other words, we see a star born here, we know that it's going to go that way on the HR diagram. Its brightness is not going to change much, but its temperature or color, it's going to go from a red star to a blue star as it gets hotter. And then something like the sun. So where's the sun? The sun is here and there. So the sun basically is going to start up here. It's going to be red. It's going to be pretty bright. But by the time it gets to the main sequence, it's actually going to get dimmer and a little bit bluer from where it starts on the HR diagram. Okay, so this is a way, again, what's the whole point of this? It's how we can determine when we see a protostar, we can tell where it's going to end up as a regular star. Why is this important? Well, because if we're trying to figure out how our sun formed, we can look back in time and find solar systems with similar stars, protostars at those temperatures, and study how they're evolving, and that can tell us about our own solar system. And then if we find similar ones, again, we can look for the elements that form life, how water ends up on planets, all the different things as we can watch those stars form their solar systems. Okay, so here's another thing. The time it takes a star to form depends on the mass. The higher the mass, the faster it burns. So stars, masses much higher than the sun's, can reach the main sequence in just a few thousand years or a million years. That's not very long. The sun, it takes millions of years for something like our sun to actually ignite, and even longer for ones with lower mass stars. And that's, again, because it takes a long time for that gravity and pressure to build up enough to begin that fusion. So we know that there's planets around other stars now, and look at these beautiful images. So you've got this disk, these disks and disks and disks around stars. So we know there's definitely material available around baby stars. Okay, yeah, and again, here's a disk and an artist's conception, and then another disk here. You can see the glowing matter, artist's conception. Okay, here is really wonderful image. This is the ALMA array, and there's a baby star right there at the center of the solar system, and you can see these dark rings forming here, and this is likely where this is what we call the protoplanetary disk. Protoplanetary disk, and the rings and the gaps indicate the presence of planets forming and sort of sweeping out. As it orbits, it's taking that material away. So this is a baby solar system, a newly formed star, and then we can see the dust as it cools and is forming planets. We can see the tracks that the planets are leaving in the material as they orbit. So that's a rare image to be able to directly image a solar system and see the stuff going on. This is only 450 light years from Earth. Okay, you can also look for do all the similar things we do with the Doppler shift and the wobble of the light and the dips in the light curves. Those type of things allow us to determine or discover exoplanets. So here's the light curve again. So that light curve dipping when a planet moves in front of it. So we talked about this light curve when two stars orbit each other, and when stars orbit each other, the light curve's a little bit different than when planets orbit a star. And so we can tell the difference between two stars orbiting each other or planets orbiting a star. And the dip is a little bit less severe when you have planets, so it's harder to measure. Okay, this is Kepler, and this was a one of the missions that was trying to study extrasolar planets. So Kepler used the light curves to determine exoplanets. This is one of the rarest images that you can get, and that's an actual solar system with actual planets. And there's one planet, a second planet, a third planet, a fourth planet, all orbiting their stars. So these are real planets orbiting stars. It's really rare to be able to do this because these things are so small and so far away that they have to be really close to actually be able to see this. So there's not a lot of images of direct imaging of solar systems, but they do exist. And again, we use this AU, because it helps us compare our solar system to other solar systems. All right, so Kepler, this is really wonderful. So these are exoplanets that have been discovered by Kepler through 2015. Obviously, we've discovered a lot more since then. But they're showing the masses in terms of Jupiters, Neptunes, and Earths. So you can see that there's a ton of planets, some the size of Earth, some the size of Neptune, some the size of Jupiter, and everywhere in between. Okay, so this is pretty wild, and this is their orbital periods. So this is the time it takes to go around the Earth. To go around the Sun. The Earth, so this is 100, that's 200, that's 300. So this would be, so these planets here are about Earth-sized. So they're about the size, the radius of Earth, and they have an orbital period of about 365 days. So, I don't know, there's 4 or 5 planets that are similar to Earth in that way. These other ones that are Earth-sized have orbital periods of 1 day to 10 days to 100 days. So that means they're really close to their stars. And so that's probably bad because that means they're not in the habitable zone necessarily of their star if they're that close to it. And the habitable zone is where you could have liquid water. If it's too hot, it boils off. If it's too cold, it's frozen. So we want liquid water on the surface, so we'd like them to be in the habitable zone of the star. But again, you can see all these different things. Wonderful. So many different planets. These are the sizes of the planets where Earth is 1. So Earth is kind of on the border here, in between here. So most of the planets we've discovered so far are larger than the planets, than the Earth, I guess, is what I'm trying to say. And these sizes of planets are not found in our solar system. They're between the sizes of Neptune and Earth. But, so that's the most probable value of planet is somewhere between Earth and Neptune in size, so about 2 times the diameter of Earth. This is really wonderful data. And these are the average number of planets per star so far that we see. Okay, one caveat. Maybe we're just not seeing all the small planets because it's harder to detect. But these are the ones, this is the number of planets we found so far. So not so many have the same number of planets as we do. It seems to be that the most common value of planets around a star is about 2. So more than 1 but less than 3. Somewhere in that range, that's the most average value. And again, we have about 8 planets around our sun. And continuing on with other things. So this is an exoplanet solar system, an extrasolar system. And so if you compare it to you've got the Sun, Mercury, Venus, Earth, Mars, and so on. This is Kepler 62, and then these are the planets that, these are not images of the planets, they're artist conceptions, but just to show you that in the Kepler 62 system, there are planets within what we call the habitable zone of the of the planets. Okay, so of the star, sorry. So how to make a hot Jupiter. Let me get rid of this. Okay, so hot Jupiters are very close to their stars. where you would think that they'd be too close to the sun, they should evaporate, and you can't explain that. Okay, so we need to figure out how you can get planets so close to the star, or we need to figure out a way to get something like Jupiter to go inward after they form and get closer to the star. And if you have that, you don't have as much of a problem. So this is just a current area of research, is why it's in here. So yeah, maybe there's a way to get a Jupiter to get closer to the sun, so then it doesn't evaporate quickly. Okay, so habitable planets are ones where you'd have liquid water and atmosphere, things like that. So we're almost getting to the point where we can measure the compositions of the atmospheres of extrasolar planets. We can get their sizes, we can get their temperatures, we can learn and infer a lot of things about them, and determine if there can be habitable planets around some of these stars. There's a planet that's about 1.3 times the mass of the sun around orbiting the M-type star Proxima Centauri, which is the closest star to us. And it could support life. It's in the habitable zone and is, I think they're trying to send some little tiny, use some laser beams to accelerate little tiny probes over to those planets and check out what's going on over there. But again, it takes 4 years for a light signal to reach us from there. So that would be it would take a while for that to happen. But if we launch it now, within our lifetimes, we could get some information about those things. Okay, so what do we got? Star formation. Make sure you understand the general idea that a ball of molecular gas collapses inward and then heats up and then forms a star. And then as it does that, it flattens out into a pancake, creating this disk. And then the disk further forms little planets among the layers there. Okay, the HR diagram, remember, it's a plot of brightness versus temperature, and there's the main sequence. But stars, protostars, will move in a certain way. They'll either keep the same temperature and get brighter, stay the same brightness or increase in temperature, or increase in temperature and get dimmer. They'll have certain evolutionary tracks where their brightness and temperature changes rapidly over, shorter lifetime scales as they form into fully fledged stars. So the HR diagram, even though it generally helps us determine stars on the main sequence, it also helps us determine the evolutionary track of stars. So that's an important thing, or how stars change over time. We know that there's planets around stars. We can use the Doppler effect. We can use the light curve effect. We can directly image them, and that allows us to count protoplanets. Kepler and Gaia are both looking for exoplanets around different stars, and so far we've found thousands of extrasolar planets that we've cataloged, and we're trying to catalog them in terms of the size of the Earth and other aspects like whether they're in the habitable zone of their star or not, to help us decide which ones to zoom in on and see if we can detect evidence of life, for example, oxygen in the atmosphere or other things like that. And then this has helped us to understand how planets form and how solar systems behave. Again, that hot Jupiter is an example of how do you get a gaseous giant so close to a star, and there's just some interesting problems to solve with respect to that. Okay, talk to you guys later.